All right. Okay. Good evening, guys. So welcome to my session. Can you guys hear me clearly? Is there any ambient noise that's
We can hear you
irritating?
clearly, Rifhan.
Perfect. Okay. So yeah, I'm Rifhan Akram, Senior Software Engineer at 99X Technology. So today I'll be talking about gRPC and microservice communication with AWS App Mesh. All right. So the agenda would look like this. So I'd start off talking about microservice communication and its challenges. Then I'll talk about what gRPC is and how it works. Then I will go through AWS App Mesh, and I'll try to spend more time on the demo. Okay, so the big monolith. We all are familiar with this type of architecture, right? We used to build applications this way, where we have the data abstraction, we have a service layer, and we have our API on top of it. All of this packaged in one big artifact. Service-to-service communication did not really happen over HTTP, right? So if you wanted, if at all there was any HTTP traffic, it was to external third-party APIs. We would package this in one big DLL or a jar, and we would deploy it behind a web server. This is how we're used to traditionally building applications. In today's world, of course, with the advancements of microservices, containerization technologies, container orchestration technologies, and so on, we have moved to a similar sort of setup like this, as you can see in the image. So where we would have microservices that are self-contained, independently deployable, and it supports a polyglot architecture, which means you don't have to build your entire application in one platform, framework, or language. If you look at the example here, the order processor service, which uses Amazon RDS, and the inventory manager service uses Amazon DynamoDB. So there really isn't any limitations of that sort, and they communicate between them over HTTP or HTTP2. One thing to remember is that microservice is not the silver bullet. So I'm not going to talk about the advantages or the disadvantages of adopting a microservice-based architecture in this talk. This is more focused about inter-service communication in a microservice architecture and its challenges. So yeah, let me start. So moving on to the challenges that we typically face with a microservice-based architecture. One is managing communication. So what is managing communication? When you have an architecture like this, as illustrated in this diagram, the services on the left are managed by team A, the services on the right are managed by team B. And they are independently deployable, so no problem, teams can work independently. But imagine a scenario where the order processor service needs to consume an upstream service called inventory manager. Now, team B is managing the API contract of inventory manager. It cannot arbitrarily go and change the API contract because team A is dependent on that contract, and there's so many other different complexities. On the other hand, for team A, they have to write the client code for the API exposed by team B. And unless and otherwise, if they're using optionally some specification like OpenAPI, they can use some third-party tools to generate client code. But still, there's going to be problems like with regards to error handling, and team B needs to implement the protocol strictly. So yeah, so then there's issues with regards to writing client code. And with regards to performance issues, so traditionally, if it was an HTTP based REST based API, you would be sending JSON over the wire, And if you take a look at this cart service example, it has 2 upstream services, and it could accumulate a lot of performance issues. The next challenge is, of course, just want to stop here and say something, guys. If you have any questions, you can ping me on the chat, or you can just just stop me and ask those questions. We can have it. We can have the session interactively running. All right, continuing. So the next challenge is service discovery. So I mentioned earlier that these microservices are independently deployable. When they are independently deployable, when they are deployed in a VPC or a virtual network, they get allocated their own private IP address. So in this example, inventory manager service has its own IP, and the consumer order processor can use this IP address to communicate with inventory manager. But team B is managing inventory manager, and team A is not aware of the changes made by team B. So if suddenly team B decides to make a change to the API, or they decide to fix a bug and redeploy, the service is going to get another IP address allocated. What happens then is the downstream order process service is going to fail because it can no more communicate with the old IP address it has. So this is another challenge coming with microservice, adapting a microservice-based architecture. All right, so the next challenge we have is observability and resilience. So with observability and resilience, this is sort of an example that we have here, where the client has a front-end service called cart service. So the client can invoke the cart service, and cart service has 3 upstream services. So tracking failure in this scenario is quite challenging. If the cart service API may be calling them synchronously or asynchronously. So if cart service fails, it may be due to cart service itself or one of the upstream services. So we really need to be able to troubleshoot and debug and find out these issues in our application, in production especially. Otherwise, it's going to be really a big issue. So if you look at how a lot of companies manage these teams, right? So typically, a team would manage 1 or more microservices. So if it was depending on multiple services, then if there's a failure happens and you had to individually go into each service and see where it failed, it's going to be a big problem. So this is where distributed tracing comes in, and we will talk. I will show you in the demo on how we could achieve this through some of the AWS services. The other is, of course, performance monitoring for upstream services. So again, if cart service is really slow, it's either because of cart service or one of the upstream services. If it's a synchronized scenario, if it's an async scenario, it can be something else. But still, we need to be able to track those performance issues. Even synchronized workloads, we need to be able to track the performance there. And next is resilience. So in a modern application, resilience is a must-have. If you look at cart service, it's dependent on 3 services. Just because one of them failing the entire operation doesn't sometimes make sense. So you need to be able to perform retries. You need to be able to perform implement the circuit breaker pattern where you can run or alternative code path or an alternative logic when a service fails. So these sort of capabilities need to be inbuilt, and trying to implement them in each service that you develop is going to be really cumbersome for small teams. And we will also be looking at how we can tackle these sort of challenges with AWS App Mesh and some of the other tools. Okay, any questions so far? I'll continue there. Okay, so that was the challenges with microservices and microservice communication. Now let's discuss what gRPC is. So gRPC is interprocess communication technology pioneered by Google. It has a binary messaging format which runs on top of HTTP2. So protobuf is a binary serialization format pioneered by Google, and that protobuf sort of contributes the most towards gRPC's performance capabilities. It's really easy. Like it's simple as invoking a local function. So invoking a remote method is simple as invoking a local function. Everything under the hood is handled by code generators. So the gRPC compilers that we have for language specific gRPC compilers that we have. gRPC is a contract first based approach. So you define your service in a proto file, and that you can use that file to generate the server side code and the client side code. So I mentioned microservice itself supports a polyglot architecture where you can have applications running in different technologies in your system. So as the gRPC supports this, as you can see in this diagram, we have the order processor service written in Node.js and the inventory manager service running in .NET Core, and they can communicate over HTTP2. So they would use the same protobuf, same proto file to generate the gRPC server and the gRPC client stub. Okay. So this is a sample proto file using the proto 3 syntax, which is the latest. So this is for a C# code base. It's simple to understand. So as you can see, I have defined an inventory management service here. The inventory management service has one RPC method called adjust inventory. It takes in one argument called inventory adjustment request that is defined here. The message type is defined here, and it returns inventory adjustment response here. So you can do a lot of things. Sometimes you might think your service file might get really big. You can break it up and import them. You can manage it centrally in a central repository. So there is so much tooling around in different languages that support that sort of capabilities. So this is the contract that we will be using to generate the gRPC server and the client. So this is a C# example because I'm more familiar with C# and .NET Core. On the top, you can see the client code. So it's just like invoking a local method. You pass in the arguments, which is accepting an inventory adjustment request object. And then this is your server. So the .NET gRPC compiler will generate this base class that you have to just extend and override the adjust inventory method, which accepts one parameter inventory adjustment request and the context. And you have to just worry about the business logic. So contrary would go look at the documentation, what sort of JSON body does it accept, what response, and so on, right? So contrary to that, this is really easy. You have everything generated. You just have to worry about this code block here, the business logic. So in this example, this is what I will be using in the demo. It's nothing much. There's a random number that's generated between 1,000 and 2,000, and I'm just going to subtract that against the parameter that I receive, quantity. Okay. So let's compare between gRPC and HTTP APIs. On the contract level, the .proto file and the service definition is required by gRPC. It's not optional. But when you look at HTTP, you have to either implement a specification like OpenAPI so that the tools can work with those. And yeah, so it's optional on that end. But in gRPC, you definitely need the service definition. The other plus is gRPC runs on top of HTTP2, so you get all the performance benefits coming with HTTP2. Payload is the biggest other benefit. So you have protobuf, which is a binary serialization format, really lightweight. So it's really fast against what you traditionally have with HTTP APIs. It has a strict specification, gRPC, and how you define your services and so on. Streaming capabilities with HTTP2, gRPC has bidirectional streaming, so you can have client and server streaming in the same service method, and then you have client streaming and server streaming. So I won't go in detail with how they're implemented or how the proto file look like. I'll attach some references so that you can have a look on how client streaming, server streaming, and bidirectional streaming is implemented. You really don't have to worry about the underlying implementation because it's handled by the generators or the compiler. You just have to worry about the logic for the most part. Browser support, yeah, there isn't much browser support, but with .NET Core, I know recently there has been some implementation with server-side reflection. So you don't have to generate the client stub at compile time. You can have it at runtime. So you can build some test tools around gRPC. Very recently, I think last week, there was a PR that got merged into the .NET gRPC open source project. Security supports TLS. You can also have authentication with JWT. So essentially, you would send that through this gRPC metadata. It's not HTTP headers, but it's again a specification that is implemented in gRPC. And of course, you have first-class support for client code generation, which is really cool. Okay. All right, let's move into AWS App Mesh. So AWS App Mesh is a managed service mesh for application level networking. It gives you support for end-to-end visibility and observability for microservices. You can also do traffic management with HTTP, HTTP2, and gRPC. So gRPC support was added only recently, I think last November. And yeah, it's pretty cool with that. And it supports hybrid deployments. So AWS App Mesh sort of looks like this. You have the App Mesh control plane at the center, so you manage configuration centrally. It uses AWS Cloud Map for service discovery. Cloud Map internally uses Route 53 for that. This center, so we would typically interact with only the AWS App Mesh control plane, and it would push its configurations to proxies that are running inside each defined service. You can have a single mesh, and you can have applications running in EKS, Fargate, ECS, EC2, Kubernetes, or even on-prem. And all of these tracing information will be pushed to AWS X-Ray. And there's also support, I believe, for AWS partnered applications. I'm not sure exactly what applications for distributed tracing, but there is support. And logs would be pushed to AWS CloudWatch. So yeah, this is the hybrid nature of it. So AWS App Mesh uses the Sidecar Pattern. So what is the Sidecar Pattern basically? This is basically, you have the control plane that is the main AWS App Mesh control plane where you interact with and where you enter your configuration. All this configuration is pushed to a proxy. So this proxy is basically another container that runs side by side with your actual application. So in this case, service A and service B is your actual application, but alongside that you run proxies. So AWS App Mesh uses Envoy, the open source project, the Envoy proxy. And this proxy is what handles network traffic, ingress traffic to your mesh and egress traffic. So this is basically our data plane, and the proxy handles all of the network traffic. And configuration is pushed to the proxy centrally. So if you want to do any networking changes, which we will try out in the demo, it would happen on the fly. You don't have to redeploy your application. So this is basically the sidecar pattern. So there's a lot of things you can do with this, right? So the main idea with this pattern is to abstract out some of the complexities, like managing networking and logging, tracing, and so on from your actual service, and delegating it to sidecar containers that run along your service. So this boundary is typically an ECS task or a ECS, an ECS task or a service. So there are some concepts that you need to wrap your head around with AWS App Mesh. First, it's the service mesh. A service mesh is basically a logical boundary for network traffic between the services that reside within it. So think it like a VPC. It's something like a VPC, right? So that's where you're going to have all your applications in. And then you have a concept called virtual service. It's basically an abstraction of an actual service that is provided by a virtual node or a router, or by means of a router. So basically, a virtual service is an abstraction of an actual ECS service. And it needs to ultimately reach to a virtual node. So it can either go directly to a virtual node or through a virtual router. A virtual node acts as a logical pointer to a discoverable service. So discoverable means you have a DNS name for your service, and from within the network, it should be able to discover itself. So you can basically say this. You can say this is basically an ECS service itself. And then you have these important concepts of virtual router and routes. So basically, a virtual router is where you can put in so many traffic management rules, like for canary deployments, like percentage-based routing, and so on. And it handles the routing there, and you can define route rules to it. So virtual gateway is something that came in recently. Virtual gateway allows resources outside your mesh to communicate with services inside the mesh. So I know this is a lot of text, so let's try to put all of this into a diagram. So this is how it will look like, right? So you have the outer bound service mesh, then your load balance interacts with the virtual gateway. Essentially, there's Envoy proxies running in it. And gateway routes will be sending out to virtual services. So virtual service can either directly connect to a virtual node or through a router. So when it goes through a router, you can define your route, right? 50% of traffic to this node, 50% of traffic to this node, or 100% of traffic to this node, so on. And you can even define retries. So if there is any failure, you can define retries. Okay, that was quick. I wanted to keep the slide simple. So let's start off with the demo. Before the demo, any other questions you have you would like to ask? Hello.
Uh,
Yeah.
Hi, Rifhan. Yeah, we can hear you. Maybe we'll
Yeah.
take the questions at the end
At the
if
end.
the
All
guys.
right.
Yeah.
Perfect. Okay. So before starting off the demo, I just want to pull up a diagram to show what the demo is going to look like. So in this demo, we are going to have three services. We're going to have an order processor service, which is discoverable through this DNS name, order processor v1.grpc-demo.local. And then we are going to have two versions of the inventory manager service, inventory manager v1 and inventory manager v2. The load balancer is going to connect to the order processor service, and order processor is going to, via gRPC, call v1 and v2. Essentially, it's going to just talk to one endpoint, and we will have AWS App Mesh handle the traffic rules. Okay, let me pull up my browser. Guys, you can see my screen, yeah? GitHub?
Yes, we can.
Okay.
Yep.
So this is the proto file. So I have my example in GitHub. I haven't written the CloudFormation scripts for the infrastructure, which I will do, which I didn't have time to, but I will definitely do it within a few days possible. So this is our service definition. As you can see, we have one method called adjust inventory, which takes in the argument of inventory adjustment request, product ID, quantity, type of adjustment, and sends out a response of inventory adjustment response, availability, and message type. This is our service definition. There's a slight change between version 1 and version 2 implementations. So let's go to the implementation. The code sample sign C#. As you can see, version 1 does not return the message. So essentially what happens is you would get, so when you, this is my load balancer endpoint, you would get an empty message. You can see the postman, right?
Yes, we can, Rifhan.
Perfect. Sorry, because I cannot see the green indicator. Okay. And the difference of implementation in version 2 is that I just send out a message. So currently, we are sending out 100% traffic to version 1. As in this example, we're sending out 100% traffic to version 1. Version 2 has sends out a message. Okay. Let's go have a look at our ECS task definitions. So I have three task definitions, one for order processor version 1 and inventory manager version 1 and 2. So let's try to map out the concepts that we discussed in the presentation in here, right? So I mentioned the sidecar pattern. This is how it's going to look like. So we have the actual service container running. Then we have the envoy sidecar proxy running. And we also have another sidecar container, X-Ray, to push out tracing information to AWS X-Ray to tackle the distributed tracing observability problems that we discussed. So you need to remember that you need to put out an environmental variable called enable envoy X-ray tracing in the envoy container so that it pushes out the tracing information. So this is the same setup across all three task definitions. And ECS, I have three ECS tasks running. Order processor version 1, inventory manager version 1, and inventory manager version 2. Okay, let's have a look at our AWS App Mesh setup. So I have the gRPC demo App Mesh setup. So this is the sort of the namespace that I'm using. So even my discoverable services start with this name. So let's start off with our virtual nodes. So I mentioned virtual nodes should link directly to ECS service. So as you can see here, gRPC-demo.local is the namespace that I'm using. And inventory manager version 1 is the host. Inventory manager version 1.grpc-demo.local is the host name for the version 1. And version 2 with version 2. It uses gRPC protocol listening on port 5000. Again, gRPC protocol listening on port 5000. It does not have any upstream services. So you need to define the outgoing traffic also. The order processor service, however, listens on HTTP on port 3000. And it has one backend service that it's calling to. So yeah, if you look at the backend, it's just going to call inventory manager v1.grpc-demo.local. So if you have a quick look at one of the task definitions and my application task definition, as you can see here, there is an environmental variable. Okay, maybe I've handled it directly hard-coded in the code. Anyway, this, oh, I looked at the wrong task definition, sorry. If you look at the order processor task definition, see, I'm only calling inventory manager v1 from my downstream order processor service. So it is not aware of a version 2 of inventory manager. It's only aware of a version 1. That's why I have defined a backend or a upstream service version 1 here to the order processor virtual node. If you look at the virtual services, I can have 3. If you look at, so this would have a typical configuration. This is where I'm more concerned about, version 1. So here currently I have a route defined, a weighted route defined. So this is, again, I have given out the name of the discoverable service, inventory manager v1.grpc-demo.local. If you look at my routing rule, it's a gRPC route. I can just define a priority. The lower the number, the higher the priority. And currently, version 1, so the virtual node version 1 gets 100% of traffic. So there I haven't made any changes. Yeah. So I have one router for inventory manager. It's the same thing that came through the service. So this is how you map all of the concepts to AWS App Mesh. Physically, there aren't any, when you create virtual sources, physically there aren't anything running, it's just configuration. So all of this configuration is transformed to a format that Envoy can understand and pushed into those containers from AWS App Mesh. So let's try out. Okay, let's try out something. So now, as you can see, 100% of traffic is going to version 1. I'm just going to randomly send a couple of requests. There is nothing returning. See, message is empty, so it's version 1. I quickly go to my service. I can do it either way. I can go to the router, go to edit. So you can manage this in code with CloudFormation. Yeah. Now I've added another virtual node. So I'm saying whenever traffic is routed through this router, we send in 50% traffic to version 1 and 50% traffic to version 2. And I save the configuration. Shouldn't take long until that is taken effect. So that was really fast, right? So configuration push to Envoy, and it's starting to capture that. So you can see in the response headers, this is coming from Envoy, and the upstream service took 22 seconds to process, 22 milliseconds to process. So that is basically canary deployments right there. So there's so many use cases with this, right? If you're migrating your workloads from ECS to Kubernetes, EKS, you can do it part by part. You can make sure that 50% of traffic is routed to the Kubernetes node, and then you can test out if it's working properly. And there's so much capabilities with how organizations function these days with continuous testing and user feedback approach, this is a really cool capability. Okay, so we spoke about how we could do this weighted routing. So there's also retries that you can implement. So, sorry. It's a bit slow. Okay. Here you could define, so you can even define certain methods to only route, right? You can give your gRPC service name. Sorry. gRPC service name. I'll try to pull up the proto file. So in here, you could give the package name dot the service name and make sure that package and certain methods are only routed there. You can have, you can define retry policies, maximum retries. So after maximum retries, it would stop routing requests there, request timeouts, and gRPC retries. So this gRPC retry is based on events, right? So gRPC has error handling protocol that it has defined, like it has its own status codes like deadline exceeded, unavailable, and so on. So based on each of those errors, you could implement retries. So that's how you would tackle that sort of scenario. Yeah, and now we have covered that part. Let me move into AWS X-Ray. So now we ran a couple of requests and we can see our service map here. So this is distributed tracing. X-Ray with AWS X-Ray, the sidecar, the container that's running along with the task is pushing all of this here. So as you can see, this is the Envoy proxy that is talking to the inventory manager service itself. And it took 3 milliseconds to consume. You can have multiple traces. You can see all of the traces here. So I have implemented health checks, gRPC health checks. So gRPC also has its own protocol for health checks. There is a service definition file. You need to implement this to implement gRPC health checks. So these are the health check calls that is sent from AWS App Mesh. I have enabled health checks. So whenever instance is unhealthy, it would go back to service discovery and say, look, I'm unhealthy, take me off when someone requests from my DNS name. And here you can see all of the traces. So version 1, version 2, how long it took, and so on. You can even plug in supported third-party tool. The documentation says so, but I haven't tried out. AWS X-Ray is so much better now, I guess. From the first time I had a look at when distributed tracing was available for serverless. Yeah, so you can see even the user agents, so gRPC traffic coming in and so on. And just a peek on service discovery. So it uses Cloud Map, and Cloud Map in turn uses Route 53 for service discovery. If you look at Inventory Manager V2, it has one service instance registered with it. So when you do DNS lookup, it returns just one IP address. But if you had 2 tasks, it would return 2 IP addresses. and your DNS client would try one, and if one fails, it would try the other IP. That's usually how DNS failover works. So CloudMap in turn creates hosted zone, a private hosted zone .3, and you have all the records, A records there as well. All right, I think I have covered everything. So yes, just sorry, just go through what we spoke. Okay, so we tried out. So we had order processor version 1 running, version 1 of Inventory Manager and version 2 of Inventory Manager, and order processor was only aware of version 1. We in the background deployed version 2 and tested version 2 and tested version 2 on the fly, and we could even take it down. We could even slowly transition to version 2, and our consumer will not know that there's a version 2. Or we could have even both running with different rules with AWS App Mesh. We tried out that. We had a look at AWS X-Ray, and yeah, so how the tracing information, response times, and all of that get pushed. And yeah, that's about it. So, any questions, guys?
Yeah, thanks, Rifan. That was a very insightful presentation. Rifan, I have a question like with regard to
Sure.
the costs aspects of it. Like, is there any additional
Yes.
costs that is being added with this Envoy proxy and the cloud map and all that, or like?
No. Yeah. So cost is basically there's no additional charge for AWS App Mesh. You only pay for the AWS resources that you consume, like ECS Fargate running, and any other resources that you consume.
Great.
No any other additional costs.
Great.
And of course, for the Envoy container that's running, that's again AWS resources.
Yeah. So I have two other questions. So one
Sure.
of the questions is, I think you guys are using this in production, right? The app mesh and everything.
Yeah. We not yet, but we are planning to getting it in
Right.
production.
Right. So earlier to this, like you were you using some kind of ECS and containers running on ECS or something like that?
Yes. Yes.
Yeah. So at what point did you decide to like you should go for app mesh, and what drives you to look for a new solution? Basically, if you can share your experience on that.
Yeah. So basically, when you have a few services running, and you have a couple of teams managing the few services, a handful, one or two is fine. You can still work with service discovery in with Route 53, and you can handle tracing by going to CloudWatch and having a look at the logs and so on. But when the number of services increase, and when there are multiple upstream services that are integrated, it's really cumbersome to troubleshoot in production. And we see a lot of advantages with AWS App Mesh as it supports hybrid deployment. So imagine just we have Fargate now, and at some point of time, we decided to integrate EKS, or we decided to move our workloads to EKS. We could seamlessly move our workloads to EKS since we have this service mesh implementation on top. So it gives a lot of advantages, and like some of the patterns I mentioned during the presentation also, uh, like circuit breaker pattern or retries, you don't have to
Yeah.
implement it in code itself. You
Mhm.
can abstract it out to the networking layer. So because they are networking problems, you can focus on the business logic.
Yeah. Awesome.
Did that
Awesome.
answer?
Yeah,
especially.
exactly. Yeah, thanks, Rifan. And my last question is,
Sure.
like, did you guys experience any delays, like when it comes to when there's envoy proxies involved, any latencies, additional latencies has been added with envoy proxy?
Yeah, there is said to be some, but it's negligible. We really haven't experienced that much of latency. It's with the advantages that comes with it, it's really a negligible amount.
Awesome. Yeah, thanks, Rifan. That was really insightful session. Yeah, guys, if you have questions, now it's the time. You can unmute yourself and ask question from Rifan.
Please do.
Hi, I'm Chamath here.
Yes.
So can we use API gateway as a ingress to App Mesh?
Currently, you can use virtual gateways, and there should be a possibility if it's discoverable. If API gateway can discover a service inside the mesh, or if it can connect to a virtual gateway, it should be able to. So I haven't played around with virtual gateway because I think it was released. The capability of talking to services inside your mesh was released only 3 or 4 days back. So I haven't really had a look at it. But based on the documentations that I checked out, you can connect a ALB.
ALB.
Yes. So I think from API gateway, you can connect to an ALB. And from there on, you can get into the mesh. I think
Okay.
that's possible.
Yeah, thanks.
Any other questions, guys?
Mm.
I think.
So
Yeah.
I have a question about that service deployment for the envoy.
Okay.
So it is supported hood deployment. You mean if you want to modify the services? That,
Yes.
so how the things happen?
It happens on the fly. So you don't have to redeploy. If you do any configuration changes, it applies on the fly like a demo. The services itself is just basic. If you're running ECS workloads, you can do ECS target deployment. So rolling updates or blueprint deployments. If you want to push configuration changes, you can push it on the fly like I demonstrated.
Okay, so another question. So is there a way to trace the Ono configurations that built from the that AWS? Is there a
Sorry,
way to?
is there a way to?
Way to trace the Ono configuration that Ono creates some Ono YAML or something that it creates the routes and the
okay, so you can define it in
everything.
your cloud formation, and you can manage it in cloud formation. So you don't basically define an Envoy YAML, but from App Mesh itself, you manage the App Mesh configuration. So App Mesh transforms it in a way that an Envoy understands.
Okay, so is there a way to track that? I mean,
Yeah, you can version control. So you mean track? You mean version control?
yeah, not version control. I mean, to see the Onoi configurations from itself.
I'm not sure you can view it through the console like I demonstrated, but
And also, what about the logging?
oh, okay. So yeah,
From the
so
Onoi side?
let me show you quickly.
Okay.
So Envoy runs just like another ECS container as a sidecar, right? And it pushes all of its logs to CloudWatch. So you can quickly go to CloudWatch. think it's easier from here. And you can view all of the logs here.
Okay.
Since it's managed, you don't have to get to this level. Like you don't have
Yeah.
to understand so much. Since it's a really managed service, so you don't have to worry too much about what Envoy does internally.
Yeah.
Does
So,
that answer your question?
yeah, yeah, it's answered. And so we can add any Envoy instances. Okay.
Yes. Yeah.
Okay.
You can add Envoy instances that run side by side with your service.
Okay, it's only supported Sidecar mode, right?
Yes.
Okay.
And as a virtual gateway.
Okay. Okay.
Guys, are there any other questions? Okay, I think there are no more questions. So thank you, Rifhan, again. That was a really insightful session. So if guys wanted to like contact you, do you have the
Yes.
contact in?
Yeah. So you can reach me out on Twitter or GitHub or LinkedIn. My information is here. And you can drop any questions on the meetup page. Be happy to answer, and I'll try to push in the cloud formation scripts within the week if time permits. So, and I'll also link up some examples that AWS has provided.
Awesome. Yeah, thanks, Rifhan, again. So I think, guys, now we can mark the end of our July meetup. Thank you very much for joining. So yeah, have a good evening. We'll see you in the August meetup as well. Thanks a lot, guys.
All right, see you.
See you.